Now let us consider the nodal analysis approach for solving the network. Uh, Actually, the nodal analysis is based on Kirchhoff's current law, okay, which states that the algebraic sum of current meeting at a point is zero. Suppose we have a resistor like this, VA and VB is the terminal voltages between the resistor R, and let I1 is the current flowing through the resistor. And how we will find the current through the resistor? Using Ohm's law. So the Ohm's law will tell you how to find the current through this resistor. So we have to find out the difference in potential divided by the resistance will give you the current. So here the current is I1 is equal to VA minus VB divided by R. That is the direct application of Ohm's law. So since the current is moving from A to B, we assume that VA is at higher potential because current always flows from a higher potential to a lower potential. If the direction of current is from A to B, then definitely VA will be higher than VB. So here we have written I1 is equal to VA minus VB by R. And now suppose if the current direction is from B to A, in that case VB will be at higher potential compared to VA. Okay, so the current equation I2 in this resistor becomes VB minus VA divided by R. So this is the basic concept. So we need to know only this concept, that the current flow is similar to a water flow. That is, current flow from a higher potential to a lower potential, similar to a water flow from higher potential, from higher level to a lower level. Okay. And now coming to nodal analysis, now let us define what is a node. Let us consider a network like this. Okay. A node is a point where two or more branches meet. Okay, in the circuit, if we analyze, there are three branches. One is the branch the branch with this 2 ohm resistor. Okay, this 2 ohm resistor. So I have written that branch as B1 here, and the second branch is the 5 ohms resistors branch, that is B2, and the third branch is this 2 ohm resistor branch. I am calling it as B3. And these three branches meet at a single point here. Okay, and this point is called the node. Okay, so a node is a point where more than one branches meet. So that is the concept of node. And now let us consider the steps to be followed in nodal analysis. The first case is, given a network, you have to identify the nodes. What are the nodes in the network? Also, you have to identify the reference node. Reference node. Okay. And then we have to name the nodes. Assume the current direction in each branch. So that is the first step. And the second step is, apply KCL at each node except for the reference node. And the third step is, for each node, you solve for the nodal equations for the unknown voltage. And the last step is, using nodal voltages, find branch current. So these are the 4 steps that is to be taken care while analyzing a circuit with node analysis. And now let us consider a typical example for this. Okay, let us consider this example. Find the current through 100 ohm resistor. So this is the question. Okay, so here first thing is we have to identify the nodes. Okay, how many nodes are here? So this branch and this branch meet at this point. So I can consider this as node 1. So I am assigning a voltage to that node V1. I am assigning a voltage to this node V1. And here this 30 ohm resistor branch and this branch 50 ohm resistor branch and 100 ohm resistor branch, these three branches meet at this particular point, and I'm assigning a voltage to this node. So this is V2, and there is one more node, and that node is this point, okay, which is nothing but a common point of all the branches. All these branches are connected to this point, and I assume that this is the reference node, which is a ground point, and this node is at zero potential. This is a reference node which is at zero potential. Reference node at zero potential. So this is the reference node at zero potential. So with respect to this node, the voltage at this point is V1. With respect to the reference node, the voltage at this point is V2. Okay. So that is the case. So I hope the points are clear. Okay. First of all, given a circuit, you assume the nodes. So here there are two nodes, and we have given the node voltages. Instead of V1 and V2, you can give it as a VA or VB, whatever value or whatever nomenclature you are interested, you can give that. But for the sake of simplicity, I have taken this as the first node and assigned the voltage as V1, and this as the second node and assign the voltage as V2. And there is also a reference node. So we are always defining the voltages with respect to the reference node, and the reference node is assumed to be at zero potential. Okay. And now let us consider the analysis of the circuit. First of all, we need to analyze the node equation for each nodes, KCL equation for each nodes. And you assume that, for the sake of simplicity, we assume that all the currents are leaving away from the node, other than the current sources direction. Other than the current sources, here there is a current source, and it is moving into the node. Other than the current sources, we assume that all the currents are leaving away from the node. Okay, all the currents are leaving away from the node. Now, let us consider, I have redrawn the first node. Okay, I have redrawn the first node. This is the first node V1, and the branches associated with this is 1 ampere, 60 volt with the 20 ohm and a 30 ohm resistor. Okay, the same circuit that we have seen here. I have redrawn the branches with the first node alone. So for first node V1, 60 volt with 20 ohm, 1 ampere and 30 ohm resistor, and this voltage is V2. Okay, I have redrawn that circuit for simplicity. And now I assume that all the currents are leaving away from the node. Okay, I assume that all the currents are leaving. So the symbol is put like this. So here also the current is leaving away from the node. So I have put the arrow direction like this. And for an independent current source, here we have an independent current source. The current source is having 1 ampere value. It is moving into the node. So let the polarity of the current of the independent current source be as such. Okay. So all the other branches, I assume that all the currents are leaving away from the node. Now I write the KCL equation at node 1. Okay, KCL equation. KCL equation at node 1. KCL equation at node. So what is this? KCL equation states that incoming current is equal to incoming. Okay, incoming current is equal to outgoing current. Outgoing current. Very simple. Incoming current is equal to outgoing current. So here the incoming current is what is 1 ampere. So 1 is equal to All other currents are leaving away from the node. So that means all other currents are outgoing. Now you write the equation, current equation for each branches. That's all. And now let me consider this branch. So what about the equation? So what about the equation? Since the current is moving from V1 to 60 volt, I assume that V1 is at higher potential. So V1 minus the terminal voltage is 60. The voltage at this point of the resistor is 60. So V1 minus 60 divided by the resistor value. Voltage, difference in voltage divided by the resistor value will give you the current. So V1 minus 60 by 20. Okay. So the current of this branch I have written. And now what about the current of this branch? 30 ohm resistor. 30 ohm resistor. So that is current is moving from V1 to V2. So V1 is at higher potential. So this outgoing current is represented as V1 minus V2 divided by 30. V1 minus V2 divided by 30. So now I have the equation with node V1. Now your role is just rewrite this equation in terms of V1 and V2 so that I can rewrite this equation like this. Okay, so first of all, let me take V1. Okay, the coefficients of V1 1 by 20, 1 by 20, and here plus 1 by 30, 1 by 30 V1, V1. And now taking the coefficient of V2 minus 1 by 30 V2 minus 1 by 30 V2 is equal to, here there is a 1, and I am taking this 60 by minus 60 by 20 onto the other side. So this becomes plus 60 by 20. Plus 60. 1 plus 60 by 20. Okay. Now, if you simplify this equation, what you will be getting is 0.083 V1, okay, minus 0.033 V2 is equal to 4. And this will be your first equation. Okay, you will get each equation corresponding to each node. Since there are two nodes in this particular circuit, okay, in this particular circuit, since we have two nodes, we are supposed to get two nodal equations. Now we got the first nodal equation. Now let me redraw the second node and the associated branches. I am redrawing the branches associated with the second node for writing the KCL equation. Okay. So I have redrawn that here, and I have assumed that all the currents are leaving away from the node. All the currents are leaving away from the node. Okay. So first of all, let me consider this branch. So here the current is moving away from V2. So the difference in voltage divided by resistance will give you the current. The difference in voltage is the difference in terminal voltage. So here the voltage at one terminal of the resistor is V2 and another terminal of this resistor is V1. So this is V1, V2 minus V1 divided by 30. So which is an outgoing current. And another one is here we have one terminal is V2. So that is at higher potential. We assume that this is at higher potential. And here there is a voltage source, and this voltage source is having 40 volt. This is 40 volt. Okay, 40 volt. So this is V2 minus 40, V2 minus 40 divided by the resistor value 50. So this current I have done. And now this current. So this is a reference potential. So that one terminal the voltage is V2 and the other terminal it is at reference potential. So this is V2 minus 0 divided by V2 minus 0 divided by 100. V2 minus 0 divided by 100. So since the reference potential is 0, we actually we won't write that. In the usual practice, we won't represent, we simply put it is V2 by 100. Since this terminal is at a reference potential, we want to put it as 0 volt. Okay, usually we will write it as V2 divided by 100. Okay, and this is equal to 0. Okay, all the currents are outgoing and there is no incoming current. So the algebraic sum of all the currents are equal to 0. Okay, now your job is to represent this in terms of V1 and V2. So first of all, I am taking V1, only this term, minus 1 by 30, minus 1 by 30 into V1. And now let me look for V2. Okay, let me look for V2. uh, Plus 1 by 30 is here, 1 by 30 is here, plus 1 by 50 is here, 1 by 50 is here, plus 1 by 100, plus 1 by 100. Okay, 1 by 100. V2 is equal to, here there is a minus, a constant term, minus 40 by 50. So if I am taking into the other side, it becomes 40 by 50. Okay, 40 by 50. Now we got an equation in terms of V1 and V2. Now you simplify this so that you will be getting a beautiful equation, minus 0.033, minus 0.033 V1 plus 0.063 V2 is equal to zero point 0.8, is equal to zero point 0.8. And this is the equation number 2. Now we have two equations in two unknowns. This is equation number 2. Now you have two equations in two unknown. Okay, now you solve for these two equations for V1 and V2, so that using any mathematical techniques, so that finally you will end up with V1 is equal to 67.25 volts, 67.25 volts, and V2 is equal to 48 volts, 48 volts. Okay, and if you know V1 and V2, if you know V1 and V2, you can find out the current in any of these branches, in any of these branches. Since if you know V1, if you know V1, what about this current? This current is V1 minus 60 by 20. Okay, and V2, what about the current through 100 ohm resistor? The current through the 100 ohm resistor is V2 divided by 100. Okay, V2 divided by 100. Since we have V2 is equal to 48 volts. Okay, V2 we have is equal to 48 volts. That is the value we got when solving the equation. So the current through the 100 ohm resistor, I 100 ohm, we consider that the current is leaving. So definitely it will be V2 by 100, V2 by 100. So this is equal to 0.48 ampere. 0.48 ampere will be the current. Okay, 0.48 ampere will be the current. Okay, so that's the solution of this network. So given a network like this, and you have to analyze it using nodal analysis, first of all what you have to identify is, you have to identify the reference node and the other nodes. Okay, then you assign values to each nodes. Okay, then for each node you assume that all the currents are living away from the node other than the current due to the independent sources. Then you apply KCL for each node. You will be getting a nodal equation for each node, and you solve for the node so that you will be getting the values of voltage, and from the values of voltage you can find out the current through any of the branches. Okay, that's all. And now let us consider another one problem. Okay, now let us consider another one problem. Let me consider this problem. Okay, you are given a network like this. Okay, I have assumed that I have given the node points also. Okay, if it is not given, you have to identify the node points. So since how many branches are connected to V1? This branch, okay, this branch, and this branch. Four branches are associated with node V1. Four branches. So definitely it is a node. And V2, how many branches are connected? 1, 2, and 3. These three branches are connected to node V2. And coming to V3, again, how many branches connected to V3? This branch, this branch, this branch, and this branch. Four branches are again connected with node V3. And there is another one node, which is the reference node. All these three branches are connected to this point. Okay, so this point is at zero potential. This point is at zero potential, or this is a reference node. This is a reference node. We assume that this as a reference node, and we assume zero potential for this reference node. Okay, and with respect to this 0 volt, this point is at voltage V1, and with respect to this 0 volt or reference node, this point is at potential V2, and with respect to this 0 volt, this point is at potential V3. Okay, now our job is to find the KCL equation for each node. You find the KCL equation for each node. Okay. Okay. Now let us analyze the network for node voltages. Node voltages. So here I am not redrawing the branches associated with each node. You assume that for each node, all the currents are leaving away from the node and write the KCL equation. Okay. Assume all the currents are leaving away from the node. Here there is no only one current source. The current source should be kept as such. The direction of the current source should be kept as such. Now let us consider the first node V1. You assume that all the currents are leaving away from the node. Okay, so now first let me consider this branch. So if the current is leaving away from the node, the current equation for this branch is V1 minus 12 divided by 4. Because while writing the current equation, always you need to write the potential difference between the two ends. Between the two ends. While writing, higher potential should come first. As higher potential should come first. Since here the current is leaving away from the node, I assume that V1 is at higher potential because current always flows from higher potential to lower potential. That is our basic assumption. Okay. So V1 minus 12 divided by 4. Okay, that current is done. And this current, this is the direction. Okay, this is the direction. So plus V1 minus V2 divided by 2. V1 minus V2 divided by 2. And now this current, the third current. Again, this potential is V1 and this potential is V3. So it is V1 minus V3 divided by 4. And now all the currents are leaving plus 9 ampere. Okay, all the terms in this equation are currents. So this is 9 and this is equal to 0. This is equal to 0. So this is the first equation what you got. Okay, this is the first equation. So while rearranging the equation in terms of V1, V2 and V3 and simplifying it, I will be getting an expression like this: V1 minus 0.5 V2 minus 0.25 V3 is equal to minus 6. So this is equation number 1. So your only job is to write the node equation following the basic principle. The rest is mathematics. Okay, simple linear algebra will suffice to solve this problem. Okay, so I hope this node equation is clear. Okay, now let us consider the second node. Now let me apply the node equation for the second node, KCL equation for the second node. Okay, okay, for the second node. The second node is V2. Second node is V2. Second node is V2. And I assume that all the currents are leaving away from the node. For each case, I am considering it as a fresh case or a fresh problem. So here, the current direction, I assume like this. All the currents are leaving away from the node V2. So now you write the KCL equation. Okay, since all the currents are leaving, the algebraic sum of all the currents is equal to 0. So let me write this equation. So here, since V2 is at higher potential than V1, so the current through this 2 ohm resistor is V2 minus V1 divided by 2. V2 minus V1 divided by 2 plus the second one. I am considering this branch. So that is the current is flowing from V2 to V3. So V2 is at higher potential. So V2 minus V3 divided by 5. V2 minus V3 divided by 5. So that current is also done. And now let me consider this. So this potential is at 0. So V2 is at higher potential. So plus V2 by 100. V2 by 100 is equal to 0. V2 by 100 is equal to 0. Okay. And now if I rewrite this equation in terms of V1, V2 and V3, I will be getting an equation like this. Minus 0.5 V1 minus 0.5 V1 plus 0.71 plus 0.71 V2 minus 0.2 minus 0.2 V3 minus 0.2 V3 is equal to 0. This is equal to 0. So this is the second equation. So you got the second equation here. Okay. Now our job is to write the third equation. Third equation. Okay. So for third node, let me consider the branches. This current is incoming. Okay. And this branch current, I assume that the current is leaving away from the node. And here I assume that current is leaving away from the node. And here also I assume that the current is leaving away from the node. So there are four terms. Only one term, one current is incoming, all the other currents are leaving. So incoming current is equal to outgoing current. KCL equation. Incoming current is equal to outgoing current. Which is the incoming current? 9 ampere current is the incoming, and the outgoing current is, first let me consider this one. Okay, V3 divided by 20. Why V3 divided by 20? Because the other point is at 0 potential, so it is V3 by 20. And now considering this one plus V3 minus V2 divided by 5. V3 minus V2 divided by 5. That is also done. Now I have to consider this branch. So that is plus V3 minus V1. This point is at V3 potential, this point is at V1. So that is V3 minus V1. V3 minus V1 divided by 4. Divided by 4. Now the currents of all the branches are considered. Okay. Now your job is to write this equation in a more beautiful form. So if you rearrange V1, V2 and V3 and simplifying, you will be getting an equation like this: 0.25 V1, 0.25 V1 minus 0.2 V2 plus 0.5 V3 plus 0.5 V3 is equal to 9. Is equal to 9. So this is equation number 3. This is equation number 3. And now you have three equations. Now you can solve these three equations for the three unknowns V1, V2 and V3. V1, V2 and V3. And once you find V1, V2 and V3, once you find V1, V2 and V3, you can solve for any branch current. You can solve for any branch current. So I hope the application of KCL uh, in node analysis, or the solution of a network using node analysis, uh, you are comfortable with the circuits. Okay. And now let me consider another one special case. Suppose you have a circuit like this. I am not going to solve this problem, but here there is a voltage source. This is a special case. Here there is a voltage source. And now if there is a voltage source like this, how will you write the KCL equation? Okay. Suppose let me consider this node voltage. This node voltage. 3 ampere is connected. So I have redrawn the node voltage V1. The node voltage V1 and the branches associated with that. Okay, this 2 ohm with voltage V2. So this voltage is important. Without voltage, you should not write the branch, draw the branch, because the branch voltage is important. The terminal voltage of each resistor is important for finding the current. Okay, so you have to write the terminal voltages in each branches. So that is important. Then only you can correctly find out the current equation in that branch. Okay, so this is the 3 ampere current entering, and here we have a 4 ohm, and this is 36 plus 4 ohm connected to this V1, and this is 2 ohm. And I assume that all the currents are leaving away from the node other than the independent source current. So I assume that this current is moving like this current is moving like this, and this current is moving like this. So how will I write the KCL equation? So first of all, incoming current is equal to outgoing current. Incoming is equal to outgoing. Outgoing. Incoming is equal to outgoing. Only one incoming, which is 3 ampere. 3 ampere is the incoming. All the other are outgoing. So since this is the reference node, it is considered at zero potential. So all the value here is at 0 volt. Okay, 0 volt. So 3 ampere is equal to, I am considering this branch, so that branch current is V1 minus 0 divided by 4, or simply V1 by 4. V1 by 4. So that is done. And now another current is, the current is moving from V1 to V2. So plus V1 minus V2 divided by 2. V1 minus V2 divided by 2. And now how will you find out this current? How will you find out this current? Here there is V1, here there is a decrease in potential. So how will you write the KVL equation? So if you write the KVL equation, it will be very easy to find out the current. So I have redrawn this branch. This branch I have redrawn. This I assume that this potential is V1, and this V3 I am representing like this. This is V3. Okay. And now I have a battery 36 volt and 4 ohm. Okay. And my job is to find this current from V1 to V3. So how will you find out? You apply KVL. So okay, apply KVL. So that is V1, increase in potential is V1 minus 36 minus 4 into I. This current you want to find out. Minus 4 into I minus V3 is equal to 0. So this is the KVL equation. Okay. From this you can find out the current. So what is that? V1 minus 36, V1 minus 36 minus V3 divided by 4 will give you the current. Divided by 4 will give you this current I. So simple. So that means voltage divided by resistance. So the total voltage divided by resistance will give you the current. So how I can find out the voltage when I am moving in this direction? Okay, here I have V1. So V1, I assume that it is at positive potential. V1 minus 36, since there is a decrease in potential, minus V3, the total voltages I have written, divided by the resistance value. The resistance value is 4. So this is the equation, the first equation. with respect to node 1. First KCL equation with respect to node 1. The similarly we have got the current equation here, V1 minus 36 minus V3 by 4. The same I have put here. Okay. So if a voltage source is coming in a branch like this, you have to follow the laws. Then you can find out the current. Okay. So that is with respect to the first node. And now similarly, what about the third node? Third node. I have considered all the branches connected with the third node. Assume that the voltage is V3, and I assume that all the currents are leaving away from the node. All the currents are leaving away from the node. And how will you write the KCL equation? And the KCL equation is simply V3 by 20, V3 by 20 plus V3 minus V2 divided by 5 plus, and how will you write this equation? Here I am assuming that V3 is at higher potential. So V3, when I am moving along the current direction, here there is an increase in potential. So increase in potential is taken as positive. That we discussed uh, when we have talked about Kirchhoff's voltage law and mesh analysis. So here there is an increase in potential. So V3 plus 36 and minus V1 divided by this 4, and all this current sum will be equal to 0. The algebraic sum of current at a point is equal to 0. So if you have any doubt of solving this branch V3 36 volt and V1, I have redrawn like this V3 36 and V1. Now you apply KVL in this branch. So KVL in this branch from this point I am starting in this direction. So V3 minus 4 into I plus 36 minus V1 is equal to 0. From this, how will you find out I? I is equal to V3 plus 36 minus V1 divided by 4. That will give you the current. The same we have written here. Okay. So writing a branch current is very important. So you have to take a special care while writing the branch current when you perform nodal analysis. And I hope these problems and the methods are clear. So thank you.